Module 30, Spiranes. In this module, you will be able to know about spiranes and their basic structure, understand their properties along with their IUPAC nomenclature. You will be able to comprehend the structural aspects of spiranes, analyze the aspect of chirality in spiranes, and assign correct absolute configuration to the spiranes. Let me tell you what are spiranes. In the previous modules, we have studied in detail about the stereochemistry of biphenyls and allenes. Now, when we consider allenes and replaces both the double bonds in allenes by rings, we obtain a bicyclic ring system in which the two rings have one atom in common. As shown in the following figure, such bicyclic system where the two rings have the same atom in common, these systems are called spiranes. The root name of spiranes is based on the number of carbon atoms in the ring structures. We use the prefix spiro with square brackets wherein we write the numbers of carbon atoms in each ring, and in such a manner such that the first number is given to the ring which is smaller in size and the second number is given to the ring which is larger in size. The size of the rings is indicated in square brackets by counting the number of atoms in the links that make each ring, excluding the spiro center. As you can see in the following spirane, the number of atoms in the links is listed in smallest first and the largest later. Let us see how we can name the following spirane. In this spirane, the functional group is an alkane. Therefore, the suffix ane is used for their nomenclature. The ring structure requires the prefix spiro, indicating the bicyclic system. The ring has a total of 5 carbon atoms, and therefore the root name pent is given. Excluding the spiro center, there are 2 carbon atoms in each ring, and hence the number 2.2 for each ring, and hence this spirane is named as spiro 2.2 pentane. Let us see another example. In this figure, the functional group again is an alkane. Therefore, the suffix ane is used. The ring structure requires the prefix spiro. The ring structure is C9 and therefore we use the root nuna. Excluding the spiro center, one ring has 3 carbon atoms and the other has 5 carbon atoms, so the numbers 3.5 will be used. There is a C1 substituent methyl group, and we number it in such a way so that it gets the lowest locant or the first point of difference. Hence, the name of this spiro compound is 1-methyl spiro 3.5 nonane. Let us see another example. In case where unsaturation is present, the same numeration pattern is maintained, but in such a way a direction around the rings so that the double and triple bonds receive numbers as low as possible in accordance with the earlier stated rules. For example, in the following figure, since the functional group is an alkene, therefore the suffix ene will be used. It has a total number of 10 carbon atoms and therefore the root name deca. There are 4 and 5 carbon atoms in the 2 rings excluding the spiro center. Therefore, we write 4.5 inside the square brackets representing the number of carbon atoms in each ring, and hence this spiro compound gets the name spiro 4.5 deca 1,6-diene. If one or both the components of a monospiro compound are fused polycyclic systems. For example, in the given figure, we have an indene ring attached to the spiro carbon atom. In such case, the spiro word is placed before the names of the components arranged in alphabetical order and enclosed in brackets are used. For example, as shown here, the numbering of the individual components is retained. You must remember that. Here the lowest possible number is given to the spiro atom, that is 1, and the number of the second component are marked with primes, here 1 prime. The position of the spiro atom is indicated by placing the appropriate numbers between the names of the two components. So, this spiro compound is named as spiro, again now in bracket, cyclopentane 1 prime indene. Let us see another example in case of monospiro compounds containing two similar polycyclic fused components. They are named by placing the prefix spiro bi, because they are the same component, so we use the suffix bi before the name of the component ring system. Now, established numeration of the polycyclic system is maintained as before, and the numbers of one component are distinguished by primes than the other component. The position of the spiro atom is indicated in the name of the spiro compound by placing the appropriate locants before the name. In this example, you can see that we have used 1 prime to number the spiro atom, and the two indene rings are joined at this point. So, the name of this compound will be 1 prime spiro bi indene. In polyspiro compounds, that means we have got more fused rings having a spiro atom, more than one spiro atoms are present in polyspiro compounds. So, they are the compound consisting of linear assembly of 3 or more acyclic systems, and they are named by placing di, tri or tetra before the name spiro. So, we can call them dispiro, trispiro, tetraspiro, etc. before the name of the unbranched chain acyclic hydrocarbon of the same total number of carbon atoms. Let us see, for example, the following figure shows a dispiro compound. Here the number of the carbon atoms linked to the spiro atoms in each ring are indicated in brackets in the same order as the numbering proceeds about the ring. Here the numbering starts with the ring atom next to the terminal spiro atom and proceeds in such a way as to give the spiro atom as low number as possible after numbering all the carbon atoms of the first ring linked to the terminal spiro atom. So, you can see here we have taken a smaller ring first, that is the cyclohexyl ring, and numbered the carbon atoms in that ring, giving the last number to the spiro atom, and then going on forward we are going to number the entire carbon skeleton. So, the name of this spiro compound would be dispiro. Then we are starting with the number of carbon atoms in ring excluding the spiro atom. So, the first ring, which looks like a cyclohexyl ring, will have 5 carbon atoms. So, we will write 5. Next dot 7, 7 is the ring for another spiro ring, and then 1, which is acting as the bridge between carbon atom number 6 and carbon atom number 8, then dot 2, which represents the bridge 16, 17. So, we will have dispiro 5.7.1.2 heptadecane. Polycyclic compounds containing more than one spiroatom and at least one fused polycyclic component are named in the same way as with earlier part of this rule, simply by replacing the spiro with the name dispiro, trispiro, etc., and choosing the end components by alphabetical order. For example, in the following figure, we have an indene ring and a fluorine ring as the fused polycyclic rings. Since alphabetically fluorine comes first, so it is numbered first, and the spiro atom attached to this ring is numbered as 1 prime, and the spiro atom joined to indene ring gets the number 4 prime, and hence this spiro compound is named as dispiro fluorine 9 1 prime cyclohexane 4 prime 1 double prime indene. In this module, we are going to discuss about various aspects of spiranes, their stereochemistry and their structural details. It is true that the structure of spiranes is firmly entrenched and the name is somewhat inapt. The name spirane, which is taken from the Latin word spira, which means twist or whirl, it implies that spiranes are not planar. It is their non-planarity that ultimately gives rise to their chirality. The two rings of the spirane, similar to the pi bonds of alene, which are just adjacent to each other, they are also orthogonal, as in the case of alenes, and the groups attached to two ends of these rings defines another planes which are at right angle to the rings which they are attached to, and also to the other groups which are attached to the other ring. So, ultimately what you are going to get is the two rings which are perpendicular to each other, and further their substituents are adjacent, they are substituents which are perpendicular to the ring as well as to the other set of groups attached to other end of these rings. This is clear in the following figure. It shows the two rings of the spirane, which is similar to the pi bonds of alene, are orthogonal to each other, and the groups attached to two ends define the planes at right angles to the adjacent ring and also to the groups attached to the other end ring. Now, following figure shows the examples of chiral spiranes. Among these chiral spiranes, one may discern three types. Let us say type A, which definitely displays axial chirality similar to that of alenes and alkylidene cycloalkanes. And another type is B, which is like corresponding alkylidene cycloalkanes and displays central rather than axial chirality. And the third, type C, which conceptually would appear to display axial chirality, but for the purpose of nomenclature it is considered to have a chiral center, as has been proposed by Can, Ingold and Prelog in 1966. Let us see this compound of type A. It is described as indicated, the descriptor is S or P. The compound B has 4 stereoisomers, that is 2 pairs of enantiomers, and C1 is the chiral center, whereas the C6 displays a cis-trans isomerism, and the stereoisomer shown here is 1s and 6 trans. To name C, the type C, one arbitrarily gives one ring preference over the other. Now, more substituted branch in that ring has a priority 1 and the less substituted has the priority 3, whereas the corresponding priorities in the arbitrarily less favored ring are given 2 and 4. Hence, the spirocenter C4 is considered a chiral center. Thus, the configuration of this stereoisomer is given as 4R. The most strained saturated spirane, the spiro 2,2-pentane as shown in this figure A, was apparently the first synthesized in 1896 by Gustavsson, although it was not then recognized as such. Its strain of 65 kilocalories per mole or 272 kilojoules per mole is only about 10 kilocalories per mole greater than that of the isolated cyclopropyl rings. Chirality in Spiranes was first recognized by Ashton in 1902, and it was demonstrated in 1920 by Mills and Nodder by a resolution of spiro dicarboxylic acid, as shown in this figure as B. This compound is of the type C, as shown in the earlier figure, where 1C4 is considered to be the chiral center. Here also the central carbon atom can be described as a chiral center. However, the compound C shown here is of the type A, as shown in the earlier figure. It was resolved 5 years later by Mills and Warren in 1925. It is shown in the following figure as C. It is of interest that the spiro center of compound C is a quaternary nitrogen rather than a carbon atom. Compound D, as shown in this figure, is also interesting. It has a spiro center and two conventional chiral centers. Now, contemplation of models indicates that existence of 3 distereomeric racemates are possible with this compound, which in fact have been isolated by Lewis and Giesler in 1912. Several assignments of absolute configuration of spiranes of the type C, as shown in the following figure, have been accomplished, and the first correct one was found out by Gerlach in 1968 and is concerned with the dione, which is shown in this figure. It is seen that it is based on that of its diol precursor. The precursor from which this dione has been made is also shown here in the same figure. The relative configuration of this diol had been established by the absence of intramolecular hydrogen bonding and also by reductive correlation with a single one of the 2 distereomeric monools. The latter result demands C2 symmetry. That is, the structures which are shown as 5 or 6 should not be true, so they are excluded. The former result, that is the absence of intramolecular hydrogen bonding, also will exclude the figure 1 and 2. Both of them are enantiomers. So, finally, the absolute configuration of the diol was established by the absence of intramolecular hydrogen bonding and also by reductive correlation with the single one of the 2 distereomeric monools. Horiot et al. Finally established Horiot's rule for assigning absolute configuration of the diol. Oxidation of this diol must lead to the S dione, which experimentally was found to be levorotatory. As you can see in this figure, the configuration of the spiro-4,4 nonane 1,6 dione has been established on the basis of the evidence that it does not have any intramolecular hydrogen bonding in its precursor diol and on the basis of correlation of the reductive pattern. In 1969, Brewster and Jones correlated the levorotatory quaternary ammonium salt as shown in the following figure as A by Stevens rearrangement. You can see the Stevens rearrangement is shown here, and considering this rearrangement to happen as superfacial, the configuration at the stereogenic carbon in the product is then correlated with that of the starting spirane. The configuration of B is in turn correlated chemically with that of S-aspartic acid, also shown in the following figure. By oxidizing the aromatic rings in B to the carboxyl group by ozonolysis, it was seen that the configuration of the levorotatory spirane has to be R. You can see that there is a spiro compound which on Stevens rearrangement give a compound B, which on ozonolysis give a compound which is similar to S-aspartic acid. So, we can establish that B was having S configuration, and since it has been formed by superficial Stevens rearrangement, the starting compound must has R configuration. The third, in principle more direct correlation of configuration of a spirane of the type C as shown in the earlier figure by synthesis from a compound with a chiral center of established configuration at first was actually did not work, and it was because of the experimental problems. The correct correlation was given by Overberger et al. In 1981, and this is shown in the following figure. You can see the configuration of the key intermediate R levorotatory A shown in this figure was established by the conversion of the sulfonamide R dextrorotatory B, whose enantiomer was chemically correlated with S-methylethyl succinic acid. The configuration of the latter had been established by Borath in 1951 by the methods of quasi-racemates. The compound R levorotatory A was then converted to a spirane plus C, which was further reduced to a diazospirane minus D by reduction. The correlation shown in this figure proves that plus C and minus D and its derived dextrorotatory spirane have R configuration. Now, there is another method apart from synthesis, that is an analytical method called circular dichroism. This method also have been used for configurational assignment of the so called NN Spiranes. Spiranes are shown in this figure. Here the N can be 6, 7 or 8. These are little complex spiromolecules and has been established, their structure has been established by using circular dichroism. These chiral compounds are notable in that they display D2 symmetry, and that the 4 ligands attached to spirocenter are structurally identical, and chirality is enforced by methylene bridges that cannot lie integrally in the planes either of the fluorine ring or of the main ring. We have seen that the structure of even complex spiranes can be determined and established either by the synthesis or correlation with the known structures or by simple analytical methods like circular dichroism. Let us summarize of what we have learned in this module. We have learned that one replaces both the double bonds in an allene by simple rings. One obtains a bicyclic ring system in which the 2 rings have one atom in common. Such bicyclic systems are called spiranes. It is true that the structure of spiranes is firmly entrenched and the name is somewhat inept. The name spirane, which has been derived from the Latin word spira, which means twist or whirl, implies that spiranes are not planar, and it is their non-planarity that gives rise to their chirality. Circular dichroism methods besides correlation methods and synthesis methods have been used for configurational assignments of various spiranes.